Let's show that the open disk is an open set. And we want to prove this as it relates to the complex plane. So let's start with, before we begin the proof, with the definition of an open set. So set S is called an open set if it is either so one of two things. The less interesting condition is if it is empty. So if it is either empty or if given any, let's say P, so point P in the set S, for some epsilon greater than 0, we have that the disk of, centered at the point P with the radius epsilon is a strict subset of the set S. So I have used the definition of what an open disk is without defining it yet, so that's what I will do now. So an open disk. So let's kind of, loosely define it. So an open disk is, so we use this notation, disk centered at a point, or the disk centered at the point P with radius R is now the set of points. And since we're interested in topology in the complex plane, we want the set of points Z such that the distance from point Z to the center of this disk is less than, and strictly less than, the radius of the disk R. And this open disk basically defines what a neighborhood, so the mathematical definition of a neighborhood of a point P, but we're not interested in that for this proof. So let's continue. Now that we've defined an open set and an open disk, let's proceed with the proof. So let's begin by letting P be a point in the disk. And this disk, let's say, is centered at the point C with a radius R. So let's say i.e. P lives inside this disk. Now, let's define, so we'll just define, just for the sake of this proof, the boundary, and acknowledge there are kind of rigorous mathematical definitions of a boundary, but we won't define it in that way. We'll just define it sufficiently for what we need in this proof. So the boundary of the disk guess, the set of points. So let's construct this set. Let's say all the gammas in the complex plane such that the distance from gamma to the center is r. And we'll just need this for one step of this proof. So now we have that the distance from P to the center is less than R. And this is since, so as a kind of, let's explain this on the side. So since gamma minus C, or that distance from gamma to C is R, and P cannot be one of those gammas, well, that is because P lives inside the disk. So because of that, we have this strict inequality here, that the distance between P and C, any point P to the center, must be strictly less than R. Okay, now it's a good time to kind of draw up a circle, a kind of illustration for our proof, and we'll kind of add things to it as we go. So let's kind of attempt to draw a circle. There we go. And so this is the open disk. Now let's, because we want, this is an open disk, we have kind of, cuts along the boundary to signal that it's an open disk. Good enough. And we have, let's change that back. Let's draw the center of this circle. Let's label that point with the point C. And we know that this has radius R. And let's join a line from the boundary of the disk, one point along the boundary of this disk to the center, going through the point P, or a point P. So let's do it here. And let's say, and we're more interested in, the points that are close to our, boundary, because they're the more interesting points in this proof. So that this illustration kind of cannot satisfy at best what our proof is trying to show, but you could kind of imagine a zoomed in version of this. So let's just draw a point P, let's say here. And we'd want this point, as I was saying, ideally close to the boundary, but for the sake of the illustration, we need a bit of, some room to work with. So this is the point P, and let's draw, a circle, and we want this circle to, merely touch No, not that. The boundary of the open disk. Yeah, that's good enough. And that's all I'll do for now, I think. Yeah, and we'll add things in as we go. So let's continue with the proof. Let's point here. Now we need to make a choice for our epsilon. So let's choose epsilon. Now this is a considered construction of epsilon, and we'll see that it will satisfy the proof as we go. So epsilon is to be, let's define epsilon to be r minus the distance from P to C. And we know that this is greater than 0. Now let's consider, let's use another value, let's say alpha, to be an element of this disk, this new disk of radius P, of center P, and I should say that P is not the one I'm referring to here. This is a general version, but the proof, I guess, is independent from that. So let's consider alpha to be a point in the disk centered at the point P with radius epsilon. And we can observe that the distance from alpha to the point P is less than epsilon. And this would work because of our choice of epsilon. Now we want to consider the points, or I guess the distance between alpha and the center, and we want to show that that is less than the radius of the open disk. Let's consider the distance from alpha to the center. We know, or I think maybe this is a good time to kind of, I guess, add in the different things into the illustration. So here the radius of this disk here is epsilon. And any point in that disk, let's choose a random point, let's denote it with alpha. I should have probably done them, labeled them with different colors, but I think it's clear enough. So that should suffice for now. So now we have this distance. So I won't be changing the value here because I'll be adding by 0 inside this absolute value. So let's subtract and add P. And normally when we do such a thing, we will use the triangle inequality to break up this absolute value. So this is less than or equal to alpha minus P plus P minus C. Okay. And I guess I should kind of, as an aside, remind us what the triangle inequality is. So when you have, so mod a plus b is less than or equal to mod a plus mod b. And if we want to illustrate this with vectors, we can draw arrows like this. Let's say this is A, that's B. This is A plus B. So I guess this, the distance when you add these two vectors together, or their magnitudes together, that will always be greater than or equal to the magnitude of this vector here. So now that we've used that, we say that this is less than epsilon plus distance from P to C because of this. And this just equals R. If you look at this, because of our choice of epsilon, if you rearrange this this equation, this equality holds here. So what have we shown? So let's write it in a line. So the distance from alpha to the center is less than R. And we can make a note that since alpha lives in the disk of center P and radius epsilon, then alpha lives in the disk of center C and radius R. Well, I should probably add here and the distance from alpha to the center is less than R. So from here, this implies that the disk of center P and radius epsilon lives inside the disk of radius of center C and radius R. So basically any point in this disk lives inside this disk. Therefore, the open disk I guess in this case it's D CR is an open set. And that completes our proof.